I'm Brendon Bradley. I'm a Professor of Earthquake Engineering at the University of Canterbury, and I'm also one of the Deputy Directors of Kaikoura, which is New Zealand's Centre for Earthquake Resilience. And so I want to take this time to talk a little bit about what we might expect in an alpine fault earthquake in terms of the ground shaking that it will cause, and then also some basic ideas in terms of the impacts that we might expect from the built environment. So I think one of the first things to understand, of course, is that the alpine fault is a major fault in New Zealand, but represents one of many different possible earthquakes that we might have. We know that we live on the boundary of the Australian and the Pacific plates, and as a result of that complicated boundary, we have many potential earthquakes that might happen. This particular image shows all of the mapped faults in the South Island region, and we know, of course, that the alpine fault is the major plate boundary, and it's important for us to try and have a single event that we can try and develop coordination in response to, but recognise that the next specific earthquake that we have that causes us damage is not necessarily going to be exactly what we planned for in advance. So for the purposes of undertaking this research and understanding the impacts that it might have, we did focus on a specific type of alpine fault event. This is what we refer to as the fjord to Kelly segment of the alpine fault. It starts, as you can see, at the southern end, just off the coast of Fiordland, and runs all the way up to around the boundary with Arthur's Pass in that region. And I'll talk a lot more in detail about some of the specific modelling that we did. But one of the first things to understand is how we can actually predict what might happen in a future earthquake in terms of ground shaking. And the main way that we do this is by developing models which allow us to both retrospectively predict what has happened in the past and then prospectively predict what might happen in the future. And one of the key data sets that we have in particular is this image that I'm showing here on the slide, which is a ground motion record, or a seismogram, of the ground motion in this particular case recorded in the middle of Christchurch during the 4th of September 2010 Darfield earthquake. And so if you look at this signal, this tells you how the ground moves in terms of its velocity on the vertical scale, and on the X scale is the time, how it evolves shaking over time. You can see that these signals are particularly complicated, and one of the challenges that we face as scientists is to try and make sense of this complicated pattern of how the ground shakes and capture the essential features so that we can predict what might happen in the future. And so throughout the South Island, of course, there's been many earthquakes, relatively large, all the way down to many small earthquakes, and each of the black points on this particular slide highlight locations where we have one of these instruments that can record that complicated pattern of ground shaking. So at each of the different black triangles in that image, we have an instrument that looks something like this, and it records the various different properties of the ground shaking. So generally speaking, the most important things that we're interested in are the three translational components, so the X, Y, and Z components of the ground shaking. And so when an earthquake happens, each one of these instruments will record some sort of shaking, as is shown there schematically in those three different directions. Now, we've recently had the 2010-2011 Canterbury earthquake sequence, and even more recently we had the 2016 Kaikoura earthquake. And so all of these events have given us this huge wealth of ground motions, and such as shown in these four images for four of the main events in the Canterbury earthquake sequence. And they're providing most of the data that we then use to develop these models to predict ground shaking, which we're obviously comparing against these past earthquakes and then using in the future to predict what might happen. One of the key features when we try and develop these models is this idea of the difference between rock properties and soil properties. And so this particular image highlights that difference in the Canterbury region. The colour, each one of those different transects is taken as a linear transect through a different part of the Canterbury Basin, and the different colour of those different parts of the rock or soil deposit tell us the stiffness or how rigid that particular property is. So what you see is that the colours that are generally red are rock properties. The darker red it is, the stiffer the rock is, and then as the colour transitions from red through to light blue and then dark blue, it means that we're moving into the soil deposits and the soil's getting softer and softer. If you look at the shape of the transition between the rock in red and the soil layers in blue, you can actually see that the depth of the soil varies over the Canterbury region. It's deepest in sort of the middle around the area of Darfield and Methven, and then it becomes shallow as you move to Banks Peninsula, for example, or also as you approach the Southern Alps. The reason why this is really important is if we look at a basic idea of how waves propagate in the Earth, and I draw an analogy here between the way that light waves propagate when they travel through different medium. If we look at a light wave as it travels through this glass lens, we see that when the light wave hits a boundary, we have three types of waves. We have the incident wave, we have the reflected wave that bounces back off the boundary, and we have the transmitted wave that travels through the boundary. Now this happens every single time a wave meets some sort of boundary between two different layers. And the reason it's important is the property between those two layers determines how much of the wave goes through the boundary and how much of it is reflected back from the boundary. So if we look at the other part now, we see that actually in this case, most of the energy is transmitted through the boundary, and because of the properties of the air on the other side of the glass, actually not only is it transmitted through the boundary, but it's bent or it's refracted as it travels through that. So this phenomena that we see here with light is exactly the same as when seismic waves travel through the Earth and they move between soil layers and rock layers, or vice versa between rock layers and soil layers. In the case of the earthquake problem, the rock layers are very stiff, they're like the glasses here, and in case of the soil layers, they're very soft, they're like the natural air is in this particular case. And so what can happen then if we take the same example and now we actually bend the boundary that the interaction occurs, we get this phenomena that we call total internal reflection, where in this particular case the angle at which that incident light hits the boundary is sufficiently large such that all of the energy is completely reflected back and none of the energy is transmitted through. And this is one of the really important things that we see when we talk about earthquake-induced ground shaking, that when seismic waves travel into soft soil basins, they tend to then hit the rock layer at enough of an angle such that most of the energy bounces back and stays within the soft soils. And so when we look at ground shaking from the alpine fault event, we'll start to see this phenomena in terms of wave energy gets trapped in the soil basins, the sedimentary basins, and that leads to shaking that's both longer and stronger than what we see when we're in areas where the rock is the predominant outcrop. So when we try and do this modelling, we really have two types of modelling tools that we want to use. One of those we call empirical models and one that we call physics-based models. And the easiest way to understand the difference between these two is to draw an analogy with weather modelling. So physics-based weather modelling is the conventional type of modelling we do. We have an understanding of the Earth's atmosphere, we have various sensors that record wind strength and precipitation and so on, and we use our understanding of atmospheric physics to predict what's going to happen in the few hours or few days. So we're now at a point where we're predicting the earthquake problem. We're starting to make use of these physics-based models and they provide us a huge amount of understanding, but more conventionally people use more simplistic empirical models. And so the weather equivalent of an empirical ground motion model is we collected today's weather for the last 100 years and we use the average of that 100 years weather from today to predict what's going to happen today. So rather than actually using our understanding of what we know now to predict the future, we just look back in time and say the average of things previously in time is what we expect the future to be. So because of this, we're now able to do some substantially more rigorous modelling using these physics-based approaches like what weather forecasting does. And the particular way that we can highlight this is if we look at some of the recent events in the Canterbury earthquakes and Kaikoura earthquakes as well. Now we all know that of course those events in aggregate have been particularly damaging, and also they've produced many of these ground motions that I mentioned are particularly important for us to be able to develop these predictive models, and so we can therefore better forecast what we might expect in the future. So this is the results of the various different ground motion simulations that have performed that tell us, for example, the strength of the shaking in the top left from the 2011 Christchurch earthquake, in the bottom left from the 2010 Darfield earthquake, and on the right hand side from the 2016 Kaikoura earthquake. Of course you can see that the scale of each of the different images is quite different. The Kaikoura earthquake on the right hand side affected a much greater geographical region than the smaller magnitude Darfield earthquake, so an even smaller magnitude Christchurch earthquake. And of course, as well as these simulation results, as I mentioned, we have all of these instruments that recorded the ground shaking, and this particular image shows the ground shaking at each one of those instruments throughout the sort of northern half of the South Island and also the lower North Island region. So if we take a look at what one of these simulations looks like for the Kaikoura earthquake, what we see is that the earthquake started in the south part in the North Canterbury area, and then slowly over time the earthquake ruptured further and further north, and each part of the fault that ruptured releases this seismic energy. And so the height of the various different waveforms that you can see there represents the strength of the shaking at a given point of time, and you can see it's moving from south to north, and there's a large amount of energy caught there. And then we want to understand how this matches with observations. So we have that particular recording station in the Wellington region, which is giving us real-time information of the shaking, and we can see how the simulation model is comparing with what we're actually observing at each of these different locations. And then, as well as looking at things from a qualitative perspective, we can also look at things from a very rigorous scientific perspective. So this slide highlights in a nutshell comparing the nature of the recorded and simulated ground motions. The black lines tell us about what was actually recorded in the earthquake, and the red lines tell us what was actually simulated. And we can look at a whole lot of different measures that summarize the strength or the duration of shaking and where the location was in order to understand the quality of those models. And so we can, based on the quality of those models, we can understand how much uncertainty we have in our particular predictions. Now, if we just keep in mind that those Canterbury earthquakes and Kaikoura earthquakes are particularly large magnitude, they caused a lot of damage, so they're really important for us to try and understand. But actually, from a scientific point of view, we make use of a lot smaller magnitude earthquakes as well, because they happen a lot more frequently, and therefore they allow us an opportunity to test our models with a lot more data. So this shows, for example, all of the small magnitude earthquakes between magnitude 3 and 5 located throughout the South Island. And then if we take all of the locations where we have recording instruments, which are shown there in blue, then each of the different earthquakes shown in red, we can draw a line between where the earthquake was and where the recording instrument was, and that sort of tells us the part of the South Island in this particular case that we're testing the model for. And so if you think of it there, all the different black lines where they all overlap tell us regions of the South Island where our model is particularly well tested, and then you see other regions where we haven't had as many earthquakes or we don't have as many recording stations, and so we have less of an ability to test the quality of our model. So looking at the particular image, you can see here that in the Canterbury region and the northern eastern portion of the South Island, we have a large enough number of earthquakes and enough number of recording stations that we really understand the properties of our model relatively well in those regions, whereas for example in Dunedin and the general eastern Otago area, both because there's not many earthquakes and also not many instruments, we don't actually have a lot of data to qualitatively and quantitatively verify and validate our model. So what does all this mean in terms of what we might expect for an alpine fault earthquake? So again, reiterating the idea that the alpine fault is the boundary of the Australian and Pacific plates across the central South Island, and that while we now, through a lot of great research from a geological perspective, have a relatively good understanding of the history of previous large earthquakes on the alpine fault, we actually, up until now, don't have a very good understanding of what the ground shaking from an alpine fault earthquake would be, because we've never had a magnitude approximately 8 earthquake in historical times in the South Island of New Zealand. And so, as I alluded to earlier, this is the specific modelling scenario that we undertook. This particular segment of the alpine fault was assumed to have ruptured, and then we wanted to understand what the ground shaking would be as a result of that particular earthquake. What we'll see is that not only the part of the fault which breaks, but actually the nature in which it breaks is quite important. And so what I mean by that is whether the earthquake starts at the southern end of the fault, whether it starts, for example, at the northern end of the fault, or whether as a third possibility, it starts at the middle, actually has quite a strong bearing on the nature of ground shaking produced, and in particular how long the ground shaking lasts for. So we considered 3 different cases there to highlight that effect, and that's what each of the 3 different stars represent, as the place on the fault where the earthquake starts. And so one of the easiest things to try and appreciate here is that when an earthquake starts, it actually begins by the rock in the fault failing at one particular point. So if this alpine fault modelling that we're doing is a 400 kilometre long fault, actually not all 400 kilometres of the earthquake breaks in one instant. It starts at an individual point and then it slowly gets bigger and bigger over time. And so actually, because the speed at which that rupture, as we call it, moves is about 3 kilometres per second, then that means in order to rupture 400 kilometres of fault, it actually requires a little over 100 seconds for that entire earthquake to happen. So the whole fault doesn't break in a single instant. And you'll see that when we look at the ground shaking, that it actually takes time for the earthquake to slowly rupture along its length. For the purpose of context, to try and keep in mind what we're talking about when we look at these great earthquakes of approximately magnitude 8, if this was the particular geometry of the magnitude 6.2 Christchurch earthquake in February 2011, and we put that same geometry, which is about 16 kilometres long and about 9 kilometres deep, in the context of the Alpine fault, then we actually, for scale, have something like this. Okay, so you can see there that when we zoom it into the right scale, the size of that February earthquake was really, really small. And so I think here's an important distinction for us to remember, that we have the magnitude of the earthquake and then we have the strength of the ground shaking. The magnitude tells us how much energy is released by the earthquake. The strength of the ground shaking depends on the magnitude, but it also depends on other factors such as how close we are to the earthquake and what type of soil conditions we're residing on when we experience that earthquake. So even though you can see here that the magnitude 6.2 Christchurch earthquake in 2011 is extremely small compared to the Alpine fault earthquake, if you are close enough to that magnitude 6 earthquake, clearly the ground shaking can be very strong and cause a lot of damage, but the area that's affected by strong shaking in a magnitude 6 earthquake is quite small. In contrast, when you have this very long 400 kilometre rupture, the area which is close to that rupture is actually significantly larger than the area which is close to the magnitude 6 fault. Okay, so it's important to differentiate that small magnitude earthquakes can still cause a lot of damage, but only in a very small area immediately near the fault, whereas large magnitude earthquakes, because of their geographic extent, cause strong shaking over a much wider area. Okay, so just to give one slide into some of the technical details about this particular problem, is that we use computational methods to try and understand the ground motion shaking over the South Island. And so essentially we discretize the South Island into a whole lot of grid of points, and at each point we solve essentially Newton's law for the equation of motion to understand how waves propagate in the Earth. So we use a little over 25 billion points to represent the South Island, and we perform this calculation using various supercomputers that exist here in New Zealand. And it's really important to appreciate the role that having access to these large computers means, because otherwise we have to simplify our problem so much to run it on small laptops that actually that simple model isn't representative of reality. And so we really need large computing resources to solve the problem accurately, such that we can provide predictions which are meaningful and we can use them for mitigation. So this is a slide which is highlighting the ground shaking from this particular earthquake. So what we see here is the earthquake occurring over the Alpine fault. This is a particular scenario where the rupture starts at the southern end. So you can see now the fault slowly breaking at the southern end. As the rupture is moving to the north with time, you can see slowly the ground shaking increases as it moves north. And what we also see is, because it's moving north at a similar speed to which the rupture is actually occurring, then we get what we call a Doppler effect, or the same sort of phenomena you experience with a landslide, that you can see the energy is backing up as it gets stacked in front of that. Now we're just getting to the point in time when the ground shaking is entering the Canterbury Basin, and so here we're seeing the phenomena that I was alluding to before, where we're getting this trapping of the basin energy. And so you can see now, despite the distance that the waves are further away in the Canterbury region, the strength of the ground shaking here is still particularly strong relative to what it is in areas outside the basin. The second thing to keep in mind is what we see in the upper right-hand corner, which is the duration of the earthquake. And so you can see here we're at a point now where we're well beyond 1 minute of shaking, and so it's important just to keep in mind that the strength of the earthquake is highlighting the fact that actually not only is it strong shaking, but actually the duration of rupture is particularly long as well. And this is one of the main differences we see when we compare small magnitude earthquakes with large magnitude earthquakes, is just how much longer the duration of shaking is. And if that amplitude of shaking is enough to start to cause some damage, then the very long duration of shaking is going to mean that we get a lot of cumulative damage, and therefore the more potential for significant impacts. And one easy way to try and understand that idea is if you have a paperclip, you can bend the paperclip once or twice and things are still relatively okay. If you repeat that bending many, many times, eventually you break the paperclip. And so we see that cumulative damage is a particularly important problem in large magnitude earthquakes where the shaking goes on for so long. What we then have, of course, as I mentioned, that the effect of the alpine fault earthquake also depends significantly on where the rupture starts. And so the previous video that we were looking at was a case where the rupture started at the southern end and slowly propagated to the northern end. And this particular video is looking at a case where now we compare side by side 3 different earthquakes on the alpine fault, where on the far left we see the rupture starting on the on the northern end. In the middle we see the rupture starting in the centre, and on the right hand side we see the rupture starting in the southern end. And so as this rupture is starting to occur with time, we see initially the earthquake start at those 3 different locations, and what we're seeing in particular is that as the earthquake starts in the middle, actually the duration at which the earthquake occurs is about half as long as when it starts either in the south or in the north. And the second thing that we're starting to see now is that actually the area that's affected by strong shaking is quite different in these 3 different cases. In the case on the left-hand side, where the rupture starts in the north, the strong shaking is only occurring predominantly in the sort of Fiordland, Southland region, whereas both for the central and the southern ruptures shown in the centre and on the right, the ground shaking is much stronger in the upper half of the South Island, and this is also the area where the population exposed is much greater as well. So those particular scenarios we expect to cause a lot more damage than the case where the fault starts in the north and ruptures toward the south. Now we can illustrate that sort of in summary by looking at these 3 images which show the strength of the shaking across all periods of time. The previous animations, of course, were showing how the shaking evolved with time. And so we see clearly what I was highlighting before, that in the centre and right-hand images, the strength of the shaking is much stronger in the northern half of the South Island, and because a lot larger portion of the South Island's population lives in both the Canterbury and sort of Nelson-Marlborough regions, then we see as a result potentially larger consequences from this. The other thing to highlight again is the fact that a large earthquake on the Alpine Fault will cause ground shaking that affects the entire South Island, and so some basic indications is that we expect MMI, or modified Mercalli intensity shaking, of 5 and above for the entire island. We expect very strong shaking, or MMI 6 and above, for about 50% of the island, and severe shaking, MMI 7 and above, for about 20% of the island. Now we know, of course, that when we have strong ground shaking, one of the significant impacts that we see is associated with liquefaction, and we've seen that in New Zealand in the recent past, both shown here on the left-hand side. The 2010-2011 Canterbury earthquakes caused both severe liquefaction but also a really large geographical extent of liquefaction. And then as well in the 2016 Kaikoura earthquake, despite moderate levels of shaking, we also saw liquefaction, in particular at the Wellington port area. Now we know that as well as causing significant damage to residential houses, liquefaction is also one of the major factors that leads to significant damage to underground lifelines. So this is just highlighting the fact that in the Canterbury earthquakes, the majority of locations where we saw damage to underground water and wastewater pipes were areas that were subjected to large amounts of liquefaction. In the context of the Alpine Fault, it's important for us to remember that not all of New Zealand is susceptible to liquefaction. The figure on the left-hand side here is illustrating the various regions which have all the way from very low up through very high levels of liquefaction susceptibility. And the figures on the right provide sort of a snapshot of that. The one on the upper right is showing us that actually when we look at the distribution of New Zealand by area, most of New Zealand is not actually very susceptible to liquefaction. A little bit more than 75% of New Zealand's landmass is not susceptible at all to liquefaction, and only a little over 5% is very susceptible to liquefaction. However, one of the important things to keep in mind is that while by area New Zealand's not that susceptible to liquefaction, we as a society tend to build in low-lying areas that are close to the coast, and therefore when we look instead not by area but by population exposed, we actually see we have a lot larger exposure to liquefaction. So the image shown there on the bottom right is highlighting the distribution of New Zealand's population that is subjected to different levels of liquefaction exposure, and we see now the portion of very high, high and moderate level of exposure almost accounts for 50% of New Zealand's population. And so when we start to think now beyond just impacts from liquefaction on the ground, but actually now to what that tells us about what we might expect to damage from buildings, the difficulty in answering this question is it very much depends both on the location and also the particular type of construction that's used. And so location is important, as highlighted on the left-hand image there, because depending on where you are in the South Island or lower North Island, the strength of the ground shaking from an alpine fault earthquake will be quite different. Where the ground shaking strength is higher, we expect on average larger amounts of damage for all types of construction. Where the shaking is lower, we expect lower amounts of damage. And then for the same strength of ground shaking, the amount of damage is then dependent on the type of construction. And so two different images that illustrate that are shown on the right-hand side, whether we're talking about residential timber houses, whether we're talking about masonry buildings, or whether we're talking about more modern concrete or steel buildings, has a strong bearing on the level of ground shaking and damage that we expect. So just a few examples of that. If we take a look at our lessons, we know from many earthquakes since the 1930s, which is when unreinforced masonry buildings were no longer constructed, but we still have many of those buildings present in our building stock. From the Canterbury earthquakes, we saw that unreinforced masonry buildings don't perform well even under moderate levels of ground shaking. However, there are various retrofit techniques that can be done, and we did see quite successful outcomes from several of those retrofit techniques. This particular slide highlights on the left-hand side, in the top left, after the September 2010 Darfield earthquake, this particular building had retrofit that you can see there with the steel bolts that are shown just sticking out from the brick wall. Had basically no damage after the Darfield earthquake, minor visible damage. Then after the February earthquake, which caused stronger shaking in the Christchurch CBD area, many masonry buildings that were unretrofitted completely collapsed, and a lot of the facades fell onto the street. You can see this particular building actually did have some relatively substantial damage, but is still upright and obviously provides sort of immediate life safety for occupants. And then because of the fact that the Canterbury earthquake sequence comprised many events, there was eventually this sort of cumulative damage, and what you can see on the right hand side is eventually the cumulative damage led to failure of part of that particular wall. Now, if we draw some comparisons there with what we might expect for an alpine fault event, in areas like Canterbury, we know the shaking from an alpine fault event won't be as severe in terms of its amplitude as what the Christchurch earthquakes were, because that Christchurch earthquake was right underneath the city. However, we know the duration of an alpine fault event will be much greater. And so if we think about each of the small magnitude events from the Canterbury earthquakes all stacked together, then the image we see on the far right, which was after many of these earthquakes in Canterbury, might be the type of phenomena that we see at the end of the ground shaking from an alpine fault earthquake, because the duration of that shaking is so much longer, even though the amplitude itself is not as strong. If we try and understand the performance of our more modern buildings, which year upon year, of course, a greater proportion of the building stock becomes more modernised, then we see from the Kaikoura earthquake, in terms of the impacts in the Wellington region, that actually when we have moderate levels of shaking, which is we expect moderate levels of shaking throughout the South Island from an alpine fault earthquake, that many modern buildings remain undamaged, or if they do sustain some damage, it's usually the interior damage to fittings and furnishings, etc. However, we do see that still multiple buildings do have sort of systematic vulnerabilities, and in the Wellington region we saw several buildings require demolition as a result. And so this really just highlights the fact that even under moderate levels of ground shaking, our current building stock isn't earthquake proof, and we really do need to exercise some extreme caution in terms of making sure that building owners and regional and local councils are always looking to improve the strength and resilience of the various buildings. And just as an example of the overall impacts from the built environment, even though the strength of the shaking in the Wellington region was relatively moderate for the Kaikoura earthquake, we did see still 11% of the commercial buildings in Wellington itself closed as a result of the earthquakes. And so we just need to understand both not the impacts immediately to the physical environment, but also then the ongoing sort of business disruption and socio-economic impacts that happen as a result of this damage incurred. So with that, I'll finish. Thank you very much.